Welcome to Fluid Mechanics, Lecture 2, Part 2 of 2. We'll go over a couple of examples of analytically computing particle paths, streamlines, and streaklines. So first, we'll consider the velocity field u is equal to minus y ex plus x ey plus ez. So the first question, if we wanted to classify this flow, is this steady or unsteady? Well, there's no explicit time dependence in any of these coefficients. We have minus y, x, and 1. So this is a steady flow. Is it unidirectional, two-dimensional, or three-dimensional flow? Well, there are three non-zero velocity components. This is the x component, ux, is minus y. The y component of the flow is uy. And the z component of the flow, uz, is just 1. So the coefficient of each unit vector is the corresponding velocity component. The coefficient of ey, for example, is the velocity component uy. And in this example, it's simply x. And since all three of these velocity components, minus y, x, and 1, are in general non-zero, except at specific points, this is a three-dimensional steady flow. So the first thing we want to compute are the particle paths. Otherwise known as path lines. So let's say that the particle location x at time 0, we'll call that x naught, is equal to 1, 0, and 0. And let's say we're interested in the path from time t equals 0 to time t equals pi. So the first thing we do is just write down the differential equation that governs the particle paths. So we recall that it's dx dt, the rate of change of the position of the point particle in time, is simply equal to the velocity u at that location and time, subject to the initial condition given above. So what we do is we break this down into the scalar components. And we get the coupled system of three differential equations, dx scalar dt is equal to ux up here is minus y, we'll call that, use capital Y, subject to the initial condition that x at time 0 is equal to the x component of this vector x naught, which is 1. You do the same thing for the y component. So the rate of change of the y location of the particle is equal to the y component of the velocity. Uy is simply equal to x, subject to the initial condition that y at time 0 is equal to the y component of the vector x naught, which is simply 0. And we do the same thing finally for the z component. dz dt, the rate of change in time of the z coordinate of the particle's location, is equal to the z velocity uz, which is simply equal to 1, subject to the initial condition the z coordinate at time 0 is equal to the z component of the initial condition vector x naught, which is 0. So if we examine this system of three differential equations, we'll notice that the first two are coupled. Because one cannot integrate the x location, or the x position of the particle, without knowing the y component, and one can't integrate the y component without knowing the x component. So these two things have to be integrated together We can do that using a matrix formulation of the differential equation, since these are linear first-order differential equations. The z component, however, is independent of both x and y, because dz dt is simply equal to 1. There's no x or y component dependence here, and so we can integrate this even without knowing the x and y locations of the particle at a given time. So, integrating this directly, we simply say that dz is equal to 1 times dt. We can integrate each side of this equation. This is about as simple as it gets. And we find that z is equal to t plus an integration constant that we'll call c3. So that's our first solution for z. The initial condition states that z at time 0, which from this is equal to 0 for time plus c3 is equal to 0. In other words, c3 is equal to 0. And the final result then is that the z component of the particle's location in time is simply time for the particle that starts at location 1, 0, 0 at time 0. If the particle started at a different location, then the result for z could indeed be different. Alright, so now let's return to the coupled equations for the x and y components of the particle location. We can write these in matrix form. We can say the rate of change in time, d by dt, of the locations x and y is equal to a coefficient matrix times x and y. So dx dt is equal to the first coefficient times x. There's nothing times x up here, so this is 0. We see dx dt is minus y, and so this second entry, the second column of the first row, will have to be minus 1. dy dt we have from the differential equation above is equal to x, so the first coefficient in the second row, so second row first column, has to be 1 because this is multiplied by x, and then the second column of the second row is multiplied by y, and from the differential equation for y, this is simply equal to 0. So this system of equations is the same as saying dx dt is equal to some matrix B times x, where x is equal to the vector of positions x, y. So the general solution to this equation is that the vector x, in other words x and y components of the particle location, this vector is equal to some integration constant c1 multiplied by e to the lambda 1 times the vector u plus another constant c2 times e to the lambda 2 t multiplied by vector v. So this is the general solution. C1 and C2 are constants that we would find by using the initial condition, the particle location at time 0. Lambda 1 and lambda 2 are eigenvalues of the coefficient matrix B, and the vectors u and v are the corresponding eigenvectors. So our matrix B is 0, minus 1, 1, 0. What we want to do is find the eigenvalues lambda 1 and lambda 2 of B. then find the corresponding eigenvectors and use that to construct the general solution for x and y. So this should be something you have already learned in a differential equations class. We'll give a quick review here for those who have forgotten it or might have claimed not to have previously seen it. So, eigenvalues of matrix B. Well, the equation to find the eigenvalues is that the determinant of B minus the eigenvalue lambda times the identity matrix I is equal to 0. So I, if you recall, identity matrix is just a diagonal matrix with 1 on the diagonals and 0 elsewhere. So lambda times I would just be lambda along the diagonals and 0 elsewhere. So now we want to take the determinant of B minus lambda I. So B is 0, minus 1, 1, 0. And we subtract out lambda I. So in other words, we subtract lambda from the diagonal entries of this matrix here. So this determinant, we multiply the entry in the first row, first column by the entry in the second row, second column, and then subtract the product of the entry in the first row, second column times the entry in the second row, first column. In other words, top left times bottom right minus top right times bottom left. We go this way minus that way for a 2 by 2 determinant. So what we get is minus lambda times minus lambda minus a minus 1 times 1, and that has to be equal to 0. So this results in lambda squared plus 1 is equal to 0. In other words, lambda squared is equal to minus 1, and then lambda is equal to plus or minus I. So let's say, for the sake of specificity, lambda 1 is equal to I, the imaginary unit. Let's take lambda 2 equal to minus I. Those are the two roots of this characteristic equation. So we have complex conjugate eigenvalues, and in fact they're purely imaginary. So the solution that we're going to take is a little bit different than the general solution we had in the previous page. So in general, if the eigenvalues lambda 1 and lambda 2 are not complex conjugates, we need both eigenvalues and both eigenvectors, or for three-dimensional motion, 3 eigenvalues and 3 eigenvectors to construct the linearly independent solutions as given by this expression here on the first page. However, when the eigenvalues are complex conjugates, we can simply choose one eigenvalue, find the corresponding eigenvector, then construct the solution to the coupled system of differential equations, the matrix equation we have here, dx and y dt is equal to b times the vector of x. We can construct the solution to that by taking the real and imaginary parts of the solution corresponding to only one of the eigenvalues because of the special case of complex conjugates. So simply, as I said, take lambda 1, so we'll let the eigenvalue equal I, and we'll find the corresponding eigenvector and then take the real and imaginary parts to get the two linearly independent solutions. Let's say lambda equals I, then we'll let the unknown eigenvector u have coefficients u1 and u2. So the eigenvector solves the equation b times u is equal to lambda u. Or if we simply bring lambda u to the left-hand side, we have b minus lambda I times u is equal to the 0 vector. So b minus lambda I, that's this matrix here we're taking the determinant of with the simple substitution that the eigenvalue lambda is equal to I. So in other words, we have that minus lambda is minus I, minus 1 is minus 1, 1 is still 1, and then minus lambda is minus I. That's b multiplied by u, u1, u2, is equal to the 0 vector. So we can write out these two equations. We get minus I times u1 minus 1 times u2 is equal to 0. So we get this is the first equation. If we do the second equation, we have 1 times u1 minus I times u2. So u1 minus I u2 is equal to 0. And we can see these two equations are linearly dependent because if we multiply the first equation by I, we get the second equation. So the eigenvector is not unique. We can only determine one of these coefficients, and we can determine the other one then in terms of the value of the first. So it's really only determined up to an arbitrary multiplicative factor. So if u is an eigenvector, some constant multiple of u, let's say a times u or 2 times u or 5 times u, is also an eigenvector. So what we'll do is say u is equal to, we'll specify the value of one component, either u1 or u2. Because the two equations are dependent, so there's only one equation to determine two unknowns. So pick the value of u1, let's say 1, and we'll solve for the value of u2 based on that. So if u1 is 1, u2 is minus I. Now, in many cases, you would normalize these to have unit magnitude, but that's a step we don't need to do here because we're going to figure out the value of the constants based on the initial conditions anyway, so that's just an extra step that provides no real benefit in this particular case. So with this value for u, we can say that a solution to the differential equation, the matrix differential equation governing x and y, this equation here from the first page, so a solution to that is simply that x and y as functions of time are going to be equal to some constant c1 u e to the lambda 1 t. And so now if we just substitute the parts, we get c1, u is minus 1 or plus 1 and minus I, and then e to the lambda 1t. Lambda was I, so we get e to the I t. And what we want to do is break this down into the real and imaginary parts. So e to the it, so if it's e to the I something, that's going to be equal to the cosine of t plus I times the sine of t. So whatever I is multiplied by, it's the cosine of that quantity plus I times the sine of that quantity when you convert e to the it to sines and cosines, if you remember some elementary, let's say trigonometry or basic math. So you have cosine of t plus I sine t. And so now what we'll do is we'll simply multiply this through and then break out the real and imaginary parts. So that's going to be equal to c1 multiplied by the real part plus the imaginary part. So the imaginary part is simply the coefficient of i's, everything multiplied by I in the expression, whereas the real part is everything that's not multiplied by the imaginary unit. So x here, x is equal to c1 times 1 cosine t plus I sine t. So the real part is cosine t, the imaginary part is sine t. For y, we have c1 minus I cosine t, so it's I times minus cosine t, so minus cosine t is the imaginary part. We have minus I squared sine t. Well, I squared is equal to minus 1, so minus I squared is equal to 1, and so we get a plus sine t as the real part here. And of course, the real part is multiplied by c1, and so is the imaginary part. a general solution here is simply a linear combination of the real and imaginary parts. So we can say that x and y is going to be equal to some constant, we'll call it c1 prime to distinguish it from this c1, times the real part, which is going to be cosine t sine t, plus a second constant, c2 prime, we'll just call it, multiplied by the imaginary part. Imaginary part is sine t minus cosine t. And now what we can do is use the initial conditions to find the constants c1 prime and c2 prime. Before we do that, I'm going to rewrite the solution, including the solution we already derived for z of t, on the next page, so we can have everything in one place for later reference. So we have x of t was equal to, from this, c1 prime cosine t plus c2 prime sine t. So we'll omit the primes just for notational simplicity. So we get c1 cosine t plus c2 sine t. Y of t is equal to c1 sine t minus c2 cosine t. And then z of t is going to be equal to sine of t plus c3. So this is going to be the general solution for the particle paths. Next thing we do is apply the initial conditions to evaluate the three constants. We've already done that for z, but we'll do them all here again just for convenience. So, initial condition, x at time equals 0 was the x component of the initial condition vector x naught, which is equal to 1. And then from these expressions here, that's c1 times the cosine of 0 plus c2 times the sine of 0. Now cosine of 0 is 1, sine of 0 is 0. So this tells us that c1 is equal to 1. Y at time 0 is the y component of the initial condition vector x naught, which was 0. And then from this expression for y, the general solution, this is c1 times the sine of 0 minus c2 times the cosine of 0. Sine of 0 is 0. Cosine of 0 is 1. And so we find that C2 is equal to 0. And then for Z, as we've already done, we said that Z at time 0 is equal to 0 from the Z component of the initial condition vector. That's equal to the sine of 0 plus C3. Sine of 0 is 0. And so we get that C3 is equal to 0. So the final result is that x of t is equal to cosine of t. Y of t is equal to the sine of t. And z of t was equal to t. I think we actually used the wrong expression here for z. So we had z is equal to t plus c3. Got a little bit ahead of ourselves for this. So this is t at 0, which gives us 0. So we still get that c3 is equal to 0, and z of t is equal to t. So I apologize for that sign of t. That comes from the next example. So these are the expressions for the particle path. Of the particle that starts at location x at time 0 is equal to 1, 0, 0. Now obviously, if it starts at a different initial location, then these equations will be different because we'll have different values of the constants of integration. Now, if we want the path from time 0 to time pi, we simply take time in the interval 0 to pi to plot the path that a particle takes. So you take a value of t, let's say 0, you substitute in here, find the x, y, and z components, plot that point. You advance t slightly, you compute the new locations, x at that new time, y at the new time, and z at the new time, you plot the second point. You do this for a whole sequence of points until time reaches pi, and you connect the points with a curve, and you have the particle path. And so this will look like a helix. It will be rotating in the xy plane. So if this is the xy plane, it'll be rotating in this direction. And because z is time, it's going to be linearly increasing in the vertical direction. So it's going to follow a circular path in the projection in the xy plane, but that path is going to keep increasing in the z coordinate. So what we end up having is the helix rising along the z axis in time. And by the time we get to pi, it's only going to be 1/2 of a cycle of 1 revolution. So it's only going to be the initial part of a helix, and it's going to look like a curve that's going halfway around the xy plane and rising a distance pi along the z axis. All right, so we've computed the particle paths. What if we want to do the streamlines? Well, the flow is steady, so the streamlines are the same as the particle paths. We can treat this t instead of time as just some parameter, so we can vary the parameter t to take values much larger than this range or much smaller than this range and plot the streamlines. That's because the streamline is an instantaneous snapshot of the velocity field. It's not restricted to be only where it goes from time 0 to pi. So you would take essentially time going from minus infinity to infinity to plot the streamline. So it would go both up and down in the z direction. And then the streaklines are also same as the paths because it's steady flow, but in this case we would take time between 0 and pi, and so we could get exactly whatever path line we plot here, get the exact same thing for the streak line because the flow is steady. So every point that ends up in the streak line follows the same trajectory through space because the velocity field is not changing in time. Alright, so that concludes the first example of steady flow. Hopefully you find it pretty straightforward. So now we'll extend this and look at the case of unsteady flow. So we use a very similar velocity field. We'll say u is equal to minus y ex plus x ey, but now we'll make the z component vary in time. So let's say z is equal to cosine of t. Or the z component of the velocity is equal to cosine t. So cosine of t is uz, x is the y component uy, and minus y is the x component ux, just as we had before. So once again, this is an unsteady flow because there's an explicit time dependence in one of the velocity components. uz is cosine of t. Because t appears there, the flow is unsteady. It's still three-dimensional because there are three non-zero components, ux, uy, and uz in general. So, first thing, particle paths. Well, if we look at the particle path equations, we find that we get something that looks exactly like we had before. The x and y components are coupled and independent of z, so there's going to be no change to those components. So dx dt is equal to ux is equal to minus y, dy dt is equal to uy, which is equal to x, and the difference is that dz dt is still equal to uz, but uz is changed, and so this is equal to cosine of t. These two are coupled. It's the same as the previous example because there's no dependence on z. So the solutions for x and y will be exactly the same. The only difference here is the z component, which in this case, once again, we can integrate this directly. So we get dz is equal to cosine of t dt. Integrate that. We find that z of t is equal to sine t plus integration constant c3. We use the initial condition. Z at time 0 is the z component of the initial condition vector. Initial condition vector here was the same as before. X naught is 1, 0, 0. That's at t equals 0. So z of 0 is equal to 0, which is equal to the sine of 0 plus c3. Sine of 0 is 0, so we get c3 is equal to 0. And we find that z is simply going to be equal to sine of t. So the particle paths x and y are just like we had before. X of t is equal to cosine of t from the previous example. Y of t is equal to the sine of t, but now z of t, as we just found, is equal to the sine of t. And so that's the one difference from the previous case. We changed the z component of the velocity because the x and y components are independent of z. Those don't change. The z component then does, of course, change. And then we take time in the interval 0 to pi to find the particle path that starts at location x naught, 1, 0, 0 at time 0 and ends up wherever it does at time pi. Why do we have pi as the endpoint? Well, that's what we were told. We wanted the particle path starting at time 0 and ending at time pi. And so that gives rise to the limits of the range of times that we want to look at. So at time pi, x will be minus 1, y will be 0, and z will be 0. Okay, the next step now is let's compute the streamline for this unsteady flow. And so it's probably best to do it on the next page. So streamline through point x naught, which is 1, 0, 0 at time t. We'll specify t later. The streamline equation, if you recall, was the derivative of the particle location x with respect to this parameter s is equal to u, which depends on x and t, subject to the initial condition that the particle location x, when the parameter s is equal to 0, is going to be equal to x naught, the initial location we're given. That's the location of the point through which this streamline is going to pass. So we break this into the scalar components just as we did for the particle paths. We get dx scalar ds is equal to ux, which is equal to minus y. Get dy ds is equal to uy, which is equal to x. And we have dz ds is equal to uz, which is equal to cosine of t. Initial conditions: x, when the parameter s is equal to 0, is equal to x component of x naught, which is 1. Y, when the parameter s is equal to 0, is equal to the y component of x naught, which is 0. And z, when the parameter s is equal to 0, is equal to the z component of the initial condition vector, or the point x naught, which is equal to 0. So these two things are coupled again, and the z component is independent of the x and y components. So we can integrate the z component directly. So now we have dz is equal to cosine of t ds, integrate both sides, but the cosine of t doesn't depend on s, it depends on time, and time is fixed when we're computing the streamlines. So we're simply integrating like this. And then what we find is that z, which depends on s, and I'll put colon time t because t is the fixed time at which we're evaluating this, is going to be equal to, well, integral of ds is s, so s times the cosine of t plus the constant of integration, which once again we'll call c3. The x and y components, they're coupled equations. We can once again write this as a matrix equation, d by ds of x and y is equal to the matrix we called B before, minus 0, minus 1, 1, 0, multiplied by x and y. We'll note there's no explicit s or t dependence on the right hand side. And so the variable with respect to which we are differentiating x and y, which is s in this case, is really arbitrary. It can be changed to any other variable without changing the meaning of this expression because s doesn't appear on the right hand side, and nor does t in this particular case. So in other words, this looks exactly like the equation we were solving for the particle path equations, except in that time we had the time derivative, and here we have the derivative with respect to s. But because s doesn't appear on this right-hand side, and because t doesn't as well, we can interchange s with t without changing the meaning of the equation. So this is exactly the same as the expression we are solving for the particle paths, and the solution is going to be exactly the same. We simply substitute t from the particle path solution to be s for the streamline solution because s is the independent variable in this particular case. So the result is that x, which depends on s at fixed time, is going to be equal to c1 cosine of s plus c2 times the sine of s. Y, which depends on s and is evaluated at a fixed time, is going to be equal to c1 sine of s minus c2 times the cosine of s. And then z of s at fixed time t is going to be equal to s times the cosine of t, times fixed, so cosine of t is just a constant in this particular case, plus c3. So that came from the solution we already integrated above. And then the x and y components come from the particle path solutions with time switched to s because of the analogous behavior or analogous form of the expression for the streamlines here and the equation we solved for the particle paths previously. So this is the general solution. We note that when we use the particle path solution for this for the streamlines, we have to go back to the general solution with the constants not yet evaluated. If you want to use the result for time, previously we found the values of C1 and C2. We had cosine t, sine t for x and y. So it would be cosine s and sine s. That would be incorrect. You have to use the most general case when you evaluate and reevaluate these constants based on the initial condition for the streamline. Doesn't matter much in this example, but in the general case it does matter quite a bit because you have two particular variables, s and t, and you want to make sure you are evaluating the constants with respect to the proper one in this particular case. So now we'll use the known location of the particle at s equals 0 to figure out the values of C1, C2, and C3. So we have that x when s is equal to 0 is equal to the x component of x naught, which is 1, which we had up here. And that's then going to be equal to C1 cosine of 0 plus C2 times the sine of 0. Sine of 0 is 0. Cosine of 0 is 1. So we find that C1 is equal to 1. Y, when s is equal to 0, is equal to the y component of x naught, which is 0. That's equal to C1 times the sine of 0 minus C2 times the cosine of 0. Cosine of 0 is 1. Sine of 0 is 0. So this tells us that C2 is equal to 0. And then z, when s is equal to 0, is equal to the z component of x naught, which is 0. And that's going to be equal to 0 times the cosine of t plus c3. 0 is obviously 0. And that tells us that c3 is equal to 0. So we can substitute the values for C1 being 1, C2 and C3 being 0 into these expressions here. We get the final result for the streamline. So streamline passing through point x naught is x of s is equal to cosine of s. Y of s is equal to sine of s. And then z of s is equal to s times the cosine of t. So we set t equal to the time at which the streamline is visualized. And then take s in the interval minus infinity, infinity to plot. And once again, you don't have to go to really extreme values of s necessarily, depending on the range of x, y, and z values for which you want to actually visualize the streamline. So the values of s you take would actually be dictated by the size of the plot window that you're dealing with. So, for example, we said before the streamlines vary with time for time-dependent flow, or unsteady flow. The streamline at time 0, we get x is equal to cosine of s, y is equal to the sine of s, and then z is equal to s times the cosine of 0 which is equal to s. So this is a helix, which is going to look the same as the particle paths that we saw previously for the steady example, or for the steady example considered initially. If we, however, look at time equal pi over 2, well, x is still cosine of s, y is still, let's make this a little clearer, y is still sine of s, but z is equal to s times the cosine of pi over 2, which is 0, and so z is equal to 0. So at time pi over 2, the streamline is actually going to be a circle, which is clearly not a helix. And so if you put in different values for t, you get different values for how z of s behaves, and you get different curves through space, which just demonstrates how the streamlines vary with time in time-dependent flow. Streamlines giving you an instantaneous snapshot of the flow based on the velocity field at that time where you're freezing it. So the first case, we're freezing it at time t equals 0, so we have a particular set of velocity components. The z component in that case is just equal to s. And at time pi over 2, the z component of velocity is equal to 0, and so the streamline would be a circle. But that's not the path the particle traces out, because as the particle moves, the velocity changes in time, and so the particle paths and streamlines are distinct. So finally, let's compute the streak line. We're going to release dye from point x0, same 1, 0, 0 as before, for time between 0 and pi. And we're going to take a picture at time pi and see what the plume of dye, or the streak of dye, looks like, and that's going to be our streamline. So what equations are we solving? Well, dx dt, the rate of change of the particle location in time, is equal to the velocity, which depends on position and time, subject to the condition that the particle location x, when time t is equal to s in this case is some parameter value, is going to be equal to x naught, which is 1, 0, 0. And then we solve this for s between the times we're looking at above. S goes between 0 and pi. So the range of times for which we're releasing dye, those are going to give you, that's going to give you the interval of the parameter s when each fluid particle passes through the point x naught. So we have the same ordinary differential equations as for the particle paths. We have, however, different initial conditions. And put that in quotes, it's not really an initial condition, it's the time when each fluid particle passes through point x naught, but it can be thought of as an initial condition. And so what we can do is we can use the general solution for the particle path differential equations, but use the new initial conditions to evaluate the integration constants. So if we go back a couple of pages, we had written general solution, I don't have it here, but we have the general solution for x and y and the general solution for t. In this case, for the unsteady flow with sine t plus c3, we can write that as a general solution and then use this initial condition to evaluate the integration constants. So the general solution we had before for x and y was the same whether it was steady or unsteady flow. X was equal to c1 times the cosine of t plus c2 times the sine of t. Y is equal to c1 times the sine of t minus c2 times the cosine of t, and then the general solution for z was equal to the sine of t plus c3. So now what we can do is apply the initial conditions. So x at time t equals s is the x component of x naught, which is 1. And that's going to be equal to c1 cosine of s plus c2 sine of s. Y at t equals s is the y component of x naught, which is 0. And that's going to be c1 sine of s minus c2 cosine of s. And then z at time t equals s is equal to the z component of x naught, which is 0. And that's going to be sine of s plus c3. So we can immediately solve for c3 from this, and we find that c3 is equal to minus sine of s. But then the solutions for c1 and c2 are coupled. So for simplicity, let's call the cosine of s c, the sine of s s. So we can write these two coupled equations as a system of equations in matrix form. So we can say that c times c1 plus s times c2, so cs, c1, c2 is equal to 1. And then the y equation is s times c1 minus c times c2 is equal to 0. So now we can solve this matrix set of equations for c1 and c2. And there are two ways to do this. I'll show you the both ways quickly here, and you can use whatever you find most convenient going forward. So one way of doing this is to solve this using what's known as Cramer's rule for solving a linear system of equations. So what Cramer's rule says is that the first constant, c1, will be equal to the determinant of this coefficient matrix with the first column replaced by the vector on the right hand side. So instead of c and s, we have 1, 0, and we retain the second column of the matrix, s and minus c, and then we divide by the determinant of the unaltered coefficient matrix, so c, s, s minus c. So if we multiply out these determinants, the first one, we get 1 times minus c minus s times 0, so we get minus c, divided by, the determinant down here is minus c squared minus s squared. And so this is equal to minus c over minus cosine squared plus sine squared of s, which is just minus 1. And so the result here is that c1 is equal to c, which is, we said before, equal to the cosine of s. And then c2 is the determinant of the coefficient matrix with the second column substituted by the right-hand side vector of this equation. So for this first constant c1, we take the right-hand side, we take that vector and substitute for the first column. And for the second constant, we take the right-hand side and substitute for the second column. So we get c, s, 1, 0. Then we divide by the same determinant of the unaltered coefficient matrix, c, s, s minus c. Determinant of this first one is c times 0. So we get 0 minus 1 times s, so it's minus s, over, it's the same determinant as before, which is just minus 1. So this is minus s, capital S, which is minus sine of s, as we said before, using our abbreviated expressions at the top right corner. So C2 is minus sine of S. C1 is equal to cosine of S. Now the other way to solve this is you can simply take these two expressions here. So we have C times C1 plus S times C2, and we have S times C1 minus C times C2. You can, for example, multiply the first equation by C. So if we do that, we get, just quickly do it down here, if we multiply this entire expression by C, we get C is equal to C squared times C1 plus SC times C2. And we can multiply the bottom expression by S, so we get 0 times S is 0 is equal to S squared C1 minus S times C times C2. We can add these two expressions together. So we get C squared plus S squared times C1, and the plus SCC2 minus SCC2 cancel out, so this is equal to the sum of the left-hand side, which is C plus 0, so that's C. And this then tells us that C1 is equal to C over C squared plus S squared. C was the cosine of S. C squared plus S squared is cosine of S squared plus sine of S squared, which is equal to 1. And so we find that C1 is equal to cosine of S just by using elimination to determine the two unknown coefficients, C1 and C2. Once C1 is known, we can use either expression 1 or C2 or expression 2 to find C2. So C2 in this case is going to be S over C times C1. So C1 times S over C is sine of S over cosine S times cosine S is sine of S. And so we would find that C2 is equal to the sine of S, or actually minus sine of S, if we keep the sign there, which is what we found here using Cramer's rule. So you get the same result, obviously, in each case because the solution is unique, and so no matter which process you use to solve for it, you get the same solution. And so whether you use Cramer's rule or whether you simply use elimination manipulating these expressions is up to you. For two equations, two unknowns, it's sort of a wash in terms of which is more efficient. But if you ever get the case of three equations, three unknowns, sometimes substitution is more difficult, other times it's actually more efficient. So whatever you like. If you like Cramer's rule, you can use it. If you don't like it, you can just use the typical elimination and substitution to find the results. So putting everything together, we know the results for C1, C2, and C3. We can substitute them into the expressions here for the streak line, and we find the expression for the streak line is going to be x is cosine of S, cosine of t, plus sine of S, sine of t. If we go back, we see cosine of S was a constant multiplied by cosine of t, and C2 is minus sine of S multiplied by sine of t. Or you get a plus. Here, so C2 should be positive. I got a typo there. Y is equal to cosine of S, sine of t, minus sine of S, cosine of t, and then Z is equal to sine of S minus sine of t. So how do we plot the streak lines? Well, we evaluate at the time when you want to actually visualize the streak line. So the time we want to visualize this is t equals pi. So you have to substitute t equals pi in each of these expressions. So cosine of pi gives us -1. Sine of pi is 0. 0 minus 1. And then sine of pi is once again 0. So the result for the streak line is that x is equal to minus cosine of s, y is equal to minus minus plus sine of s, and then z, if we get z correctly, z is equal to sine of t minus sine of s, so we have this backwards. It's sine of t minus sine of s, so z is equal to minus sine of s. So these are the expressions for the streak line. Then we let s vary between 0 and pi to plot. So we note here, if we take the particle location, x at s equals 0 is equal to minus cosine of 0, which is equal to minus 1 sine of 0, 0, 0. And this is not equal to point x0, which is equal to plus 1, 0, 0. So when you set s equal to 0, this is not the point x0. S equals 0 actually corresponds to the endpoint of the streak line, the point furthest away from the place where you're releasing dye or tracer particles. If we looked at x when s is equal to pi, we'd find that we get minus cosine of pi. Cosine of pi is minus 1, minus minus 1. We get plus 1. Sine of pi is 0, 0. And that's equal to x0. So x0 corresponds to s equals pi, the end time, whereas s equals 0 corresponds to the end point of the streak line. And the reason this happens is, let's say this is our point x0. We start releasing dye or tracer particles when time, well, at the beginning of time, so s is equal to 0. And so the first particle is released here, it flows along and it ends up at some location here at time t. A particle later on is released here and it ends up somewhere over here at time t. At a later interval, when s takes a larger value, we release the particle and it ends up over here. And so you connect the endpoints of these different particle paths, and that is what corresponds to the streak line. So when s is equal to pi, and we take the picture at time pi, we release the tracer particle or the smoke here, the dye here at time, or when s equals pi, we take the picture at the exact instance released, so it hasn't had anywhere to go. So the end time, or the end point of s, corresponds to the original point, or the origin of the streak line, whereas s equals 0 corresponds to the terminal point of the streak line. That's in theory the furthest away from the point where you're releasing the particles. And it doesn't have to be furthest in distance, but it's furthest in arc length along the streak line. This because the flow could curl back around and approach the point again. So one of the key things to keep in mind for the streak line is how the initial conditions differ from the case of particle paths. So we saw before, it's the same equations as particle paths, so same set of differential equations, so the same general solution, but different, quote, initial conditions. So the particle location when time equals at s is at the point where dye, smoke, or tracer particles are being released, x0. So then once we get the general solution for the streak line, you then have to substitute for time, the final time, in this case time equals pi. That's the time when you're taking a picture, the time when you're visualizing the flow, in order to evaluate those coefficients.